Hello? Yeah, it's working. Hi, welcome to the talk that's named Reflection or Reflection. Most of what you will see today has been sponsored. I mean, we did the research during our office hours, so I think it's legitimate to have some advertising for Groupon, and yes, we're recruiting. So my name is Stéphane Nicolas. You can follow me on GitHub, Stack Overflow, Google+, if there are still some users. I'm a senior Android developer at Groupon. I got something like 20 years of Java coding experience, and on the open source side, I'm one of the contributors of RoboSpice, RoboJuice, Boundbox, Inject, Start, a couple of projects like that. So the talk today is going to be about reflection, about annotation processing and optimizations related to this. We will start by explaining the motivations behind this research, and then we will go in depth into reflection, trying to find alternatives to reflection, because there are some issues in Android, as you might know. And after that, we will propose one solution, which is named reflection, no reflection, like a bird, no wing. I've been told it's poetic, don't know. And finally, a conclusion on this research. You should have some kind of background knowledge of dependency injection and bindings. By bindings, I mean stuff like Bottoknife, Dart, Vitamin Saber, and annotation processing also. I'm not going to go very deep into explaining that, so I hope that you got some basic knowledge of that. So the motivations. At Groupon, we maintain a dependency injection framework that's named RoboJuice. RoboJuice is actually not only a funny library because it has a funny logo, but it's also a very feature-rich dependency injection framework because it's based on Juice. Juice has almost 10 years of existence now. And yeah, it's really feature-rich. You can do a lot of stuff with Juice very easily. It's very easy to configure and use. And actually, there is even, in most cases, in the simplest cases, there is no need for configuration at all. And one of the big advantages of Juice compared to Dagger, to name it, is that there is no manual graph definition. So you don't have to do it by yourself inside your own application. You don't have to care about the graph dependency, the dependency graph, because Juice is going to handle that for you. So Juice and RoboJuice are great, but actually it is slow. Why is it slow? Because it's based on a reflection. And in Android, since the very beginning, there has been some issue with reflection. Now the issues have been solved partially, but there are still some troubles. And I think even Dart introduced new ones because of the compilation ahead of time. Just to go fast on that. So with Art, you can compile the code ahead of time. When you install the application inside the device, it's going to be compiled directly to native code. But you cannot do that with reflection because the name of the method or the field that you're going to try to access may be a variable. So it cannot be compiled ahead of time. It needs to be estimated at compile time. That's one of the things that can explain why reflection is a bit slower than normal code on the Android JVM. So RoboJuice is slow? Okay, so we tried our best to improve performances, and with the release of RoboJuice 3 last year, we could gain up to 35% of improvements in speed, which is actually very good. I'm not going to go very deep into the details, but you can find some slides on Speaker Deck on how we did that. Basically, what we did is just turning RoboJuice, which was purely based on Juice and depending only on reflection, into some kind of hybrid library that uses also annotation processing to filter the usages of reflection, so that we use reflection only when we need it. And the annotation processor is going to tell Juice, okay, now you will need to use reflection for this field, this method, and this constructor. No more. So we try to target the usage of reflection, not to use it for nothing, basically. So yeah, we could gain like 35% speed improvement, but how does it compare to other dependency frameworks? So let's say you got a class A with a single dependency B, very straightforward, empty classes. So if you want to create 100 instances of A with the dependency B, if you use new A, which is also going to trigger the creation of the dependency of an B, then if you do that 1,000 times, it almost takes no time. If you do it directly, like new A, it will create a new B at the same time, and it's super, super fast, nothing to say here, almost 0 milliseconds. If you use Dagger 1, then it will take like 10 milliseconds. If you use RoboJuice 2, up to 27 milliseconds, something like that. RoboJuice 3 with 35% improvement lowered it to like 16, 17 milliseconds. And with RoboJuice 4, we find a couple of new optimizations, but still we are close to 15, not close to 10. So it improved, but not enough really compared to Dagger 1. Though, yeah, you can also wonder if those numbers are really, if they do really matter. I think that's an open question, because 1,000 injection, it doesn't happen very often, but still, it would be nice to be as fast. So, if our understanding of the problem of juice is correct, the problem of juice and RoboJuice is that reflection is slow. Yeah, reflection is slow. So, the simple solution would be to, oh, I got a problem with, yeah, animations. Yeah, so let's try to kill reflection completely. That was like our main motivation. So first, let's try to understand what is reflection. So I hope that most of you are familiar with this concept. So let's say you got some Java source code. The basic flow when you build an application is to take the Java source code inside your IDE, to send it to the compiler. It will provide bytecode that will be executed on the JVM. And then you will get a running application. Reflection happens at that level here. So it means that during its life, when the application is going to be running, the application can access to a description of itself in terms of classes, methods, fields, and constructors. So we can access to this description of itself, and we can also change the application. So it's not only a read-only view of the application that we get via reflection, but also a writable image of the application. And we can change the values of fields, we can invoke methods, invoke constructors via reflection. Here is a simple example of a few usages of the reflection API. So as you can see, it's very intuitive, very close to the way humans or developers talk about our object-oriented programs. So you're going to manipulate classes, which are represented by the Java class. You're going to manipulate constructors. You can invoke them. You can access methods in the same way and invoke them passing parameters. You can also discover the parameters of a method or a constructor. You can also access the fields by their name, and you can get the value of a field for a given instance of an object, and you can also set the value of this field for a given object. So, yeah, reflection is slow, but what exactly is slow inside reflection? I think this question is quite important, so let's break down this into pieces. As you can see on those graphs here, when you try to access a field by reflection, instead of accessing the field directly, it's like 3 times slower on a Dalvik machine. So all of this has been benchmarked in milliseconds on Genymotion, which is a very good implementation of JVM, very useful for testing. So if you access a field 1 million times, you can see that it takes around 1 milliseconds for direct access, and via reflection, 3 milliseconds, so a bit slower. On the lower right side, the graph is about methods invocations, so you can see that still it's a bit slower via reflection. And for constructor accesses, this graph shows that there is a huge difference between reflection and direct access. So if you create a class directly by using a new in your code, it's going to be very, very fast and so slow using reflection. So that should be something to try to target, to bypass reflection, at least for constructors. But if we could also bypass reflection for accessing fields or invoking methods, that would be nice too. On the lower right, you can also find a graph that represents the time that's taken to do a few basic operations using reflection, like class loading, so using basically class.forName and a string. So you load a new class into the memory, into the JVM. And as you can see, this operation is pretty slow compared to like direct access of a method or constructor, whatever. So it takes a lot of time to load a new class into memory. In the same way, when you are scanning fields or scanning methods inside a given class, for instance, to look for annotated fields or annotated methods, then it takes also some time, less than loading a full class, but still, it's a bit slow. So, yeah, we wanted to try to find a way to bypass that, to completely avoid reflection, so that Juice, maybe hopefully Juice, and even all other libraries based on reflection could be faster on Android. So let's see, what can we find as alternatives to reflection? So if we take the same schema that we saw earlier, the reflection happens at runtime, but there are some alternatives to get a view of the program and to be able to manipulate it. For instance, we could use bytecode weaving. So bytecode weaving is something that you can do at the bytecode level, for sure. And you can modify this bytecode, which is pure binary. You could change inside whatever you want. You could, for instance, create a new field, create a method, whatever. And so this is an alternative possibility to get a view that is writable of the application. Another option could be to use abstract syntax trees. So we will come into more details about what they are and how to use them. And the third option that we studied is actually well known and very trendy on Android, at least for the last 3 years maybe. It's annotation processing. So let's go deeper and study all of these alternatives. So the first one is bytecode weaving. So you might be aware that in Java there are 2 ways to do bytecode weaving. The first one is to do bytecode weaving at runtime. So basically what happens, and many Java technologies rely on that. So when you load a class into the JVM, you can use what is called a user agent. And this user agent will intercept the bytecode that is being loaded into the memory, into the JVM. And at that very precise moment, you can manipulate the bytecode, change it, add methods, add new code, do whatever you want. But on Android, this is not possible because there is no agent on Dalvik and Art. So the only option left to manipulate the bytecode is static bytecode weaving. By this, we mean to change the bytecode right after the compilation. So Javac is going to produce new bytecode files, .class files, and we are going to open those files and manipulate them directly and ship them into the DEX that's going into your APK, basically. So here is an example of what we could achieve using bytecode manipulations. Let's take a single activity, this very simple one, and you just annotate it with @log lifecycle. So once this gets compiled, we provide this bytecode to a transformer, I think we call that. And now we detected that you added this annotation, and we can change the bytecode according to that and perform a certain number of actions. For instance, here, we're going to look at all the methods that are related to the lifecycle of the activity and log them so that in ADB logcat, you would get the time spent for each method call that is part of the lifecycle. You could also see which one is called and which one is not called. So it's very easy to use. You just use a simple annotation. So we've been working on that for like 3-4 months. We've created a full stack, which was a bit complicated because we also to be interoperable between Gradle, Maven, then use Java Assist, and provide like basic libraries to manipulate the bytecode, do it at the Android level, etc., etc. So we did a full stack, and you can find it in GitHub, Stéphane Nicolas /injects. And you will see we have a bunch of projects like that to inject views, to inject resources, all this just by bytecode weaving. So this approach is feasible. But let's evaluate it maybe more completely. So it's very simple to use, as you can see, just a single annotation, and it can be very, very powerful. It's as easy to use as a Gradle plugin. There is no boilerplate required, so you just add an annotation, that's it. Very powerful because you have access to the bytecode, so you can do whatever you want, even things you don't want to. For instance, you can very easily create a method with 2 return statements. At the bytecode level, no one is going to prevent you to do so. The Java compiler for sure is going to forbid that, but when you are at the bytecode level, there is no help. You are on your own, basically. So you can do whatever you want. It's extremely powerful. And there is also kind of a standard in Java to manipulate bytecode, which is called Java Assist, and we could reuse that to perform manipulations of bytecode also for Android. On the dark side, let's say that what happens with bytecode weaving is that it's very complex. So when you want to write a new library, it's very difficult. You got a full stack of libraries to use. It's difficult to figure out exactly who is going to do what, who are the responsibilities of the different layers inside the stack, how to manipulate bytecode even by itself. It's a bit tricky, a bit mysterious even sometimes. And Java Assist has some missing features also. So yeah, it's difficult. But we think that the main problems come from the fact that it's not standard. So it means that inside the huge bit task graph that you got when you are building an application via Gradle, for instance, I don't know if some of you have already seen the graph, but actually it's huge. It has over 100 nodes. So there are over 100 operations that are performed by Gradle when you build an application. And inside this huge task graph, there is no real place to do my bytecode manipulation. So as soon as the build process is going to change on Android, you're going to have to adapt the bytecode weaving libraries, which is quite tricky and also very tricky to support 2 versions. So indeed, it requires a high level of maintenance to keep that stack going. Also, one of the limitations is that Java Assist is issued from the Java world, so it can manipulate very easily class files and jars, but not dexes. So it means that if some of the libraries you're using are coming in the form of AAR, for instance, you won't be able to do any bytecode manipulation inside those libraries. For your own code, it's possible, because you are going to manipulate the .class file, but not for some of the libraries if they don't come as jars. An open question, which is actually a very limiting factor, is that Google has been announcing maybe like 1 year ago that they are going to change the whole tool chain because they want to provide a more incremental tool chain that would be more aware of incremental changes, so that if you change some part of the source code, only this class file is going to be replaced, only this part of the DEX is going to be changed, only this delta is going to be submitted to the device, and so that the whole tool chain is going to be much faster. So yeah, it's expected, it's even experimentally working, you can activate that inside your Gradle build, but up to now, we don't have any information about the formats that is going to be used by Jack and Jill to perform this operation faster. We know that there is a format called JACE, but no one has any detail on that. And if you look at the implementations of Jack and Jill inside the Gradle plugin, you can see that it changes very, very, very quickly. Much faster than the pace of change of the documentation, which is quasi non-existent. Also, a disadvantage of bytecode weaving is that modifications are not visible, so it can, let's say, be a bit precarious for some developers. What we are doing is that we manipulate the bytecode, so inside your IDE you won't see any change. You've typed something, your program is the way you typed it, but we are going to manipulate the bytecode that is produced after the compiler is working. And you won't see these changes. You won't see the changes inside the IDE. You can only see them if you retro engineer via JavaP your class files. So you're not going to be aware of that. To my mind, it's not a very big issue if the libraries are tested enough, but it can be some kind of black point, let's say, for this technique. One of the alternatives was AST manipulation. So I don't know if most of you are aware of that. Abstract syntax trees are indeed a format in which all the compilers that compile Java source code into .class files are going to represent all the Java statements. So when you compile a class file, the source file is going to be first represented as an AST, an abstract syntax tree, and then this tree is going to be turned into a class file. This works for all the compilers. We will see that there are some subtle differences sometimes. So here is an example. Again, you just annotate a class that implements parseable. And you can see that we just declare a field inside. There is no need for creating the creator, the parcel creator, or creating the describe content method. All of this is going to be generated just by IST manipulation. So this is very powerful. In the Java world, you got a very well-known project that is called Lombok. So Lombok, you just annotate a field with @getter, @setter, and they will generate the setters and getters for you. And for Android, a guy I met last year mentioned that he's been working on some kind of fork of Lombok and applying it to Android. That's one of his of his examples. So you can find also this project on GitHub. If we evaluate IST manipulations, it will more or less be the same as bytecode weaving. So it's very simple to use, no boilerplate at all, very easy to use because there is a Gradle plugin, even an IDE plugin in this case. So you can see some of the changes, let's say. It's extremely powerful as bytecode weaving. But when it comes to create a new library, it's actually even harder than bytecode weaving because you have to manipulate abstract syntax trees, and they are not normalized by the GDK, the Java specifications. So they are indeed non-standard. By non-standard, I mean that there are two compilers in the Java world. One is for Eclipse compiler for Java, and the other one from the GDK, which is Javac, Java-C. And both of them do transform source code into ASTs, and then ASTs into .class files, but they use different implementations of ASTs. So what Lombok has been doing is that it has been providing two implementations of all its features, one for ECJ, the Eclipse compiler, and one for the JDK. Again, maybe on Android, yeah, that's right, we could also just maybe focus on Java-C and drop Eclipse. I think no one uses Eclipse anymore, hopefully. And yeah, so that could be possible. So maybe it's not such a disadvantage. Still, the Jack and Jill problem is going to be the same as for bytecode weaving. We don't know exactly about JACE, so we don't know exactly if there are still going to be even some ASTs or not. Maybe JACE is just going to be ASTs serialized. Many people have wished that for a long time for Java itself. But we don't know, and we don't know how AST manipulation is going to evolve with the new toolchain. And modifications are not really invisible, but let's say we don't see much. You can maybe see new getters and setters in the project structure if you inspect your class, but you won't be able to see the bytecode that has been added, so not the implementation of those methods. The third option was annotation processing. So here you got an example of annotation processing with butter knife. We just bind a few fields like to associate them to some fields inside your XML, some tags inside your XML layouts. We do the same for a few resources, on clicks, and so on. And as you can see inside the onCreate method of your activity, you will have to create this statement, to write this statement, butterknife.bind this. So this is pure boilerplate code. It's used to link your own code with the code that is going to be generated by annotation processing. So yeah, this is pure boilerplate. You wouldn't like to have to write that, but it's still needed. And actually it uses reflection, which is interesting because some people think that when you use annotation processing, you don't use reflection at all, which is not exactly true. So let's evaluate what annotation processing gives us. Oh, it's too fast. Huh. Does it work? Yeah. So yeah, annotation processing is quite simple to use. You just have to annotate a bunch of fields, methods, whatever. It's a Java standard, which is a big plus. So it's part of the Java specification. It's not supposed to change. It's supposed to be implemented by all the Java compilers, and it's supposed to work in the same way for everyone, which is good. It's relatively powerful, not as powerful as bytecode weaving or AST manipulations. We will see why in a second. One of the drawbacks of annotation processing, I don't know if some of you have tried already to write annotation processors. How many in this room have tried to do so? Did you find it easy? So. Actually, I think the API is really difficult. Why it's difficult? Because we are very familiar with the way that reflection works, because it's very close to the way that we do understand a Java program. But when it comes to annotation processing API, the view you got of the program is much closer to the view that the compiler has of the program. And so it's very difficult for us to understand what is an element, a type element, primitive elements. They are not exactly the same thing as reflection. Also, one of the drawbacks of annotation processing is that it's completely impossible to modify code. This is done by design, so there is no way you can actually modify existing source code with annotation processing. The only thing you can do is to generate new code. Yeah, there are some acts you can do to actually modify the behavior of your code, but yeah, that's not very interesting. But still, you cannot modify your code. That's what we wanted to try to do. What it means when we have to come to annotation processing instead of reflection, it means that every library that is based on reflection, that was supposed to be working like hell on Java, working super well, like Jackson, Jackson 1, Jackson 2, JSON, all those good libraries that are tested, made sure have been used for years, they all have to be rewritten completely to use annotation processing. And that's what happens now in the Android world. We are obliged to write completely new libraries for doing everything. For parsing Jackson, for parsing JSON, for parsing XML maybe, for ORM discoveries, or yeah, even for dependency injection for sure. So we have to write every new library again. Another thing that is not so interesting about annotation processing is that as you generate new code, you cannot change the bytecode, you cannot change your existing source code, so you will have to get some kind of glue between the generated code and your own code. So you need boilerplate to invoke generated code, which is something we would like to avoid. So let's get a deeper look at annotation processing, try to understand better what we are using it for on Android. So we take a Java source file, we pass it to the annotation processor. It's going to generate new Java source code, and both the Java source code generated and your code are going to be passed to the compiler and be compiled at the same time. If you look at what the generated code looks like, here you got a very simple activity about Groupon. It's a Groupon activity, so it's a good activity. And then you got some fields that are bound inside this activity. When we pass it to Butterknife, it will generate this class, which is about Groupon, so the same name as the activity, $$, viewBinder. And inside this class, that is completely generated by the annotation processor, you will find some code that actually performs the glue or assigns all the fields from XML to the fields of your activity. So this is what is generated. So basically, we use generated code in all the libraries that use annotation processing to do three things. The first one is to access fields, so read fields or assign fields, call methods, and call constructors. All those members can be accessed at one condition: they must be non-private. Because you cannot modify the source code of, you cannot modify existing source code, and existing source code is the only one to have access to private members. It's not possible to access them via something else that is generated. So you have to remove the private modifier, which is actually violating some of the very basic principle of the object-oriented programming. So yeah, what we do, if you look at that, is doing exactly the same thing as Reflection is doing. So we came up with an idea to try to unify that and to get the best of both worlds with a new project that we called RNR, Reflection No Reflection. The objectives of RNR are, first, to make it easy to adapt reflection-based libraries into Android. So we don't want to have to rewrite everything that has been performing well for years. We would like to be able to reuse these technologies. Second, we'd like to get the best of both worlds. So the ease of reflection that talks to us because it speaks the same language as we do, and annotation processing because it provides a lot of speed. And three, generated code is not very interesting for no one, so we would like to hide it completely. So we came up with an idea that we can summarize in one sentence, is that we would like RNR to generate reflection-like code via annotation processing. So we'd like to use annotation processing to generate something that you as a developer, or you as a library maker maybe, will be able to use like Reflection very easily. That's the basic idea. Now, let me explain you the internals of RNR. We got a picture? Cool. So, in Reflection or No Reflection, we're going to perform three steps. The first one is to define what we call RNR classes that are 100% compatible with Reflection API. So we will have our own class that represents a class, our own class that represents a method, our own class that represents a field and a constructor. We want to get exactly the same API, which is very easy to test automatically. You can test the coverage and see that your API matches the true native Reflection API. And we are going to fill those classes, all the information required by Reflection, we are going to fill those classes with information that we can acquire during annotation processing. So during the first step of annotation processing, we build something that is roughly equivalent to Reflection. That's the first step. Second step, we're going to take those RNR classes and generate code so that they can be also created at runtime. So they will become available at runtime. In the first step, they will become available at annotation processing time. In the second step, we're going to generate them so that even an application that is running can use them. We will come back into more details into those steps. And the third step is to allow, via generated code, to allow modifications of members, access fields, invoke methods, and constructors. So if we could make those three steps work, we would actually have something that is completely equivalent to Reflection, but not using Reflection at all. Hence the name of this library. So the first step is to, during annotation processing time, to create the R&R classes. So we are going to take an annotation processor of our own from our library, create those R&R classes, and then after that, once this is done, then as a developer, you could create an annotation processor that is going to be using reflection API instead of the annotation processing API, which is difficult to handle. So once we get that, we can go on with the normal cycle of annotation processing and generate Java source code, pass it to the compiler, and it will get compiled as well as your original source code and produce a class file. Is that clear? Yeah. So what are the results that we get outside of the first step? So it means that as a developer, you can manipulate fields, methods, constructors, and classes before they are compiled, which is kind of a, yeah, I really like this idea. So you're going to compile something to get classes, fields, and methods, but before getting them compiled, you will be able to use them for creating an annotation processor. So it will be much simpler. So it's kind of a unification of annotation processing and reflection API at the annotation processing time. And we think that by itself, it's kind of an important theoretical achievement in Java. Let's see what step 2 is. Step 2, we're going to make those R&R classes accessible at runtime. So we're not going only to create those classes and take them into the JVM during annotation processing time. We're going to generate code so that those R&R classes become available at runtime. So you take your Java source code, you pass it to our annotation processor, then we're going to generate code that will fill the R&R classes. So we fill the R&R classes for our own, so we got all those classes into memory, the whole description of the application, and we are also going to generate code to do the same thing at runtime. So all the information that we acquire during annotation processing is going to be accessible during runtime of the application. So we pass this code to the compiler, and now the application, when it's running, will be able to access the R&R reflection instead of true reflection. Here is, oh yeah, there is one thing. So if you do that, you will get, during runtime, you will be able to get access to the R&R reflection, but this reflection, those reflection classes are going to provide you a read-only view of the application. It means that you will be able to get the classes, to get the fields, to get the members, like methods, constructors, everything, but you will not be able to invoke methods. You will not be able to access fields. You will just get like the rough structure provided by API reflection, the API of reflection. What does R&R class look like when it's generated? It's very straightforward. Now we define a class by giving it a name. We can add fields. We can add annotations to these fields. We can add methods in the same way. We can add modifiers to all the fields that we have discovered during annotation processing. So it's basically a very readable version of the API of reflection. So this code is going to be generated, and at runtime, your application or any library will be able to access those classes. Those classes are 100% compatible with reflection API classes. They are filled during annotation processing and generated to become accessible at runtime. So that's step 2. If we look at what we get outside of step 2, it means that all the R&R reflection classes are now available for libs and applications at runtime. They will provide a read-only access to reflection information, so still not able to access fields of instances, invoke methods of instances. And they are faster than reflection because they don't use true native reflection. They just use pure Java statements, and actually they are exactly the equivalent of what is generated by any library like Butterknife or Dart. So yeah, everything is working well, but they are read-only, unlike true native reflection. So we are missing like very important features of reflection, the ability to change the value of a field, to invoke a method of a given instance of a class. So we're going to remedy this by step 3. In step 3, we're going to provide write access to the reflection, R&R reflection API. How do we do that? So we still take your source code, generate this code in step 2 for generating field R&R classes, and we're going to also generate what we call class reflectors. Class reflectors will allow us to provide not only a read-only view of reflection during runtime, but now, thanks to the reflectors, we're going to be able to write or to modify the application via R&R reflection classes. So you will be able to access fields, you will be able to invoke methods. What does a reflector look like? It looks like that. So we got a simple class A with 1 or 2 fields, a constructor. Here is what a reflector for this class looks like. So as you can see, there are like 3 or 4 methods. One to change the value of a field, change the value, get the value of a field, invoke a method, invoke a constructor, or multiple constructors if you have multiple constructors in your class. So it's only very simple Java statements that are generated during annotation processing, so they should be tremendously faster than reflection, and they are roughly equivalent and provide you with all the features of the reflection API. So as the result of step 3, we now got something that extends a bit what step 2 provided. We are now able to access all the features of reflection during app and runtime. We provide a read and write access to reflection information, and it's faster than reflection in Android. Yeah, by the way, there was a little detail we gently omitted, is that if you look at what reflection does when you inspect a field, you got a field by a reflection, you can ask the field, what annotations do you have? What are you annotated with? And the answer provided by the API of reflection is going to be an instance of this annotation, providing you all the values of the annotations. This is actually a bit tricky, because if you think about it, an instance of an annotation, what is that? An annotation is actually something that extends an interface, so the Java compiler is going to provide an implementation of those interfaces so that at runtime, your reflection API will be able to get those instances and work with them. And we did exactly the same thing. So we passed the details, but we were pretty proud when we achieved that. So now we got R&R working. It's been, quite a lot of job, but it works. So what's next? Our main focus during this research has been to improve the performances of dependency injection. So our basic idea, still a bit stubborn, is to, let's say, we try to fork Juice and see how it goes. So usually the way we've designed it, we would have hoped that it would be very simple. Just replace every reflection call, true native reflection call, by our R&R reflection calls. And that's it. We just changed the imports. We had this idea in mind. It should not be very difficult to fork a library like Juice. Well, if we look into some details, so actually Juice uses reflection for processing. So all the information that is provided by reflection is used for Juice to process, what to inject, how to compute the dependency injection graph, and so on. So here, Juice uses reflection. It uses also reflection to access fields, to invoke methods, and to create instances. What we did in the fork of Juice, that we called R&R Juice, is that we used R&R for processing, accessing fields, invoking methods, and creating instances. So in a whole Juice, which is quite a complex library, we just switched from the true native reflection to R&R reflection, and see how it goes. Here you can see something like not really using reflection to scan classes members, because in Juice and R&R Juice, since RoboJuice 3, I told about it a bit earlier, we use somewhat an hybrid system using annotation processing to limit the scanning of class members. So it's not really reflection, but also some annotation processing is being used. So how has it been? Well, actually, this was a failure, and quite a big one, which was very disappointing. So what happened and why did it fail is that Juice uses a lot of features of reflection. It's all based on reflection, and it uses reflection so much. We actually learned a lot about reflection when we tried to do that. So when we forked it to replace reflection by R&R reflection, it came up that we had to introduce quite a high volume of changes, which means potential bugs. And Juice is so complex that we were not confident at all that this code could even be running. Also, we've faced some unexpected troubles, like something that we just understood a bit later is that reflection is not only an API like others for the Java language. It's also very, very related to the compiler and to the language itself. So if you look at those statements here, we got a simple class A, an instance name A. When we do a class.forName A, this is a reflection call. In the same way you could say instance.getClass, and this is also a reflection call. And what you would get is exactly the same thing as a.class, which is not a reflection call, which is actually a compiler understood directly by a symbol understood directly by the compiler. And there is no way we could do this kind of equivalence things with our own reflection classes. So we've been like hitting a wall. Okay, when you hit a wall, what do? You try again, no? So we tried again, and now we had this idea that we wanted to minimize the amount of changes in juice and use RNR only to bypass native reflections for member access via reflectors. So we just use that. Instead of the whole machinery of RNR, we're just going to use reflectors to just at the very end, not use reflection, but use our stuff, which is supposed to be faster. So we did that, and only that. The fork was easy. We got good performance results, actually almost like 20% improvements when creating instances of a class via the second fork of juice. But this is not really accurate, because when you create a lot of generated code, you also have to load this code into memory, and it takes time at startup. So we are doing great when we are running the application, but at startup, the time was slightly increased, and it actually even destroyed all the gains we could gain by pure speed improvements. So, and it adds also a lot of complexity. So it's not really a success. At a conclusion, for step 1 of RNR, we think that it should be possible to unify completely annotation processing and reflection at compile time. So maybe that's something that's interesting for the Java community at large, or even for new languages like Kotlin, or new languages that would like to design their annotation processing APIs and reflection APIs so that they match each other, they are easier to remember, easier to use, more compatible, and so on. As a step 2 and step 3, we think that it's just a generalization of all the work that has been done on Android recently during the last 2-3 years, where a couple of new libraries have been introduced and we're using annotation processing to circumvent usage of reflection. We think that RNR demonstrates that this approach is feasible, but actually not so much paying back. So we initiated this research to achieve a faster dependency injection for Android. We didn't really get to that point, but it was interesting, and I think we've been very far in exploring annotation processing and reflection. We plan to release a new version of Juice and RoboJuice based on RNR reflectors, because there are some improvements. We're not sure yet exactly how we are going to do that and when. We got to decide on that. And we wanted to share that with you so that you got a better idea of what annotation processing means, how it could be unified with reflection, why those APIs are similar or different, and what are the alternatives. Do you have any questions, comments? Yeah. Thank you very much, by the way. Yeah, cool.
So one of the problems that we're running into with our app for reflection is JSON, or it seems like every JSON parser is actually doing reflection.
Yeah, not all of them. Sorry. Yeah.
Jackson does not, but Jackson has a large startup cost to instantiate that original object mapper. So I'm curious if you did any research on the JSON aspect of it.
Yeah, sure.
Remove the reflection from JSON.
Yeah, our idea was not only to improve the performances of dependency injection by improving the dependency of juice and recycling it into RoboJuice. We think that our research had a broader scope involving JSON parsing, for instance, or M-Lite usage on Android, which is a bit limited by reflection as well. So we investigated that. And there are indeed some new libraries that came up, like Logan Square. I don't know if you're aware of this one, but it's actually performing very well and not using reflection at all, just using annotation processing and streaming API. Yeah?
Yeah, so using the Jackson mapper under the hood?
No. It uses, it uses the streaming API of Jackson.
So,
Yeah.
we're able to actually instantiate Jackson up front.
Uh-huh.
We were working on performance at start time.
Mm-hmm.
We're seeing that the amount of gain that we had from Logan Square actually being faster to parse JSON.
Uh-huh.
We were losing by how long it took to instantiate Logan Square the first time.
Yeah.
Instantiating the Jackson parser. So
Yeah.
what we found was that JSON actually does it the fast. If we can remove the reflection from JSON,
Mm-hmm.
start time is super fast.
Mm-hmm.
And JSON, there's no way right now not to do reflection. It always accesses the fields by reflection. So if that call is gone, I mean,
Yeah,
like the biggest gain in Android right now.
Mm-hmm. Yeah, and we think that too. we actually are a bit surprised that this problem is not addressed directly by Google, but it looks like they have other issues to address. But yeah, it would be an improvement even for Jackson parsing or MLight, but as the results of Juice with the fork with R&R are not so exciting, I don't think we're going to pitch ourselves in forking Jackson too. Yeah. Yeah. How many objects and methods are created by generated code? Okay, so the question is about the number of methods created by generated code. I guess that's your concern is the DEX limit. Yeah, so indeed you create, like, as you could see with reflectors, like 3-4 methods per classes that you want to use during reflection. So it ends up to be like 4 times the number of classes that will use R&R, the answer. So in our application, we are also struggling not to use multi-DEX because it's slower. So we are also trying to take a lot of care not to bypass the DEX limit. And actually, yeah, we got like maybe 2,000 new methods counting in, which is a lot for us. So it's also one of the drawbacks. So yeah, we can gain like 10%, but we're going to increase our DEX, the number of methods in our DEX, increase the complexity of Juice. Not sure it's worth it. But yeah, that's also one of the limiting factors of the annotation processing approach at large. When you think about it, butter knife is going to add a good number of methods, same for Dart, same for everything. So if you do it for, yeah, systematically for all your technologies, like JSON parsing or MLight and so on, you will add a lot of generated code that will like decrease your DEX limit, and you will have less space for your code. So yeah, it's something to take into account. You're right. Any other question? Maybe just to finish, I'd like to say that we think that the true solution, what we have been trying to do, is to patch actually some deficiency of the GVM on Android. So it should be done at that level. So it could be possible to get exactly the same thing as Java does. It means that we could inline all reflection code, not with ahead of time compilation, but with just-in-time compilation, like a PC GVM does. So yeah, that could be a solution. Also, yeah, the compiler also could do the dependency injection, but that's kind of a different way to approach the solution. Thank you very much.